Hello there, and welcome to this quiet corner of the universe. Tonight, we aren't simply stargazing. We're drifting toward our neighbor galaxy, Andromeda, a vast spiral of stars, dust, and dark matter spinning slowly in space for over 10 billion years. But beneath its distant beauty lies secrets, ancient collisions, a double nucleus, and a supermassive black hole that sleeps in silence. We'll travel gently from its warped spiral arms to its mysterious core, from globular clusters older than time to the inevitable collision that will reshape our cosmic neighborhood. Now, let's begin our quiet journey to Andromeda. Andromeda is the most distant object you can see with your naked eye. On autumn nights, when you look up at the constellation Andromeda, that faint smudge of light you might glimpse is actually a galaxy containing over 1 trillion stars. The photons entering your eyes tonight began their journey 2.5 million years ago, when our early human ancestors were just learning to make stone tools. This light has been traveling since long before Homo sapiens existed, crossing the void while life on Earth was still learning its first tentative steps toward consciousness. When that light began its journey, the climate was cooling toward an ice age, and the ancestors of humans were small-brained hominids learning to use primitive tools. The light you see tonight is ancient beyond measure, a messenger from a time when Earth was a very different world. The earliest known record of Andromeda was written in 964 CE by the Persian astronomer Abd al-Rahman al-Sufi, who described it as a small cloud in his book of fixed stars. For centuries after, astronomers looked at this mysterious patch of light without understanding its true nature. When Simon Marius observed it through a telescope in 1612, he was the first to see its structure magnified, though he still had no idea he was looking at another galaxy entirely. For hundreds of years, astronomers believed Andromeda was a nebula, a cloud of gas and dust within our own Milky Way. It wasn't until the 1920s that the great debate about the nature of these spiral nebulae was finally settled. Harlow Shapley argued they were part of our galaxy, while Heber Curtis insisted they were separate island universes. The debate raged until Edwin Hubble, using the powerful Hooker telescope, identified Cepheid variable stars in Andromeda and measured their brightness to calculate the galaxy's true distance. This revelation forever changed our understanding of the universe. Suddenly, we knew we lived in just one galaxy among countless others scattered through space. The cosmos became unimaginably larger, filled with island universes stretching to the very limits of observation. Andromeda was the key that unlocked this new vision of reality. The first galaxy proven to exist beyond our own. Andromeda spans an enormous 152,000 light-years across, possibly even 220,000 to 260,000 light-years if we count its full stellar disk. To put this in perspective, if you could see Andromeda's true extent in the night sky, it would appear more than 6 times wider than the full moon. Yet most of this vast structure remains invisible to our eyes, hidden in darkness, too faint for human vision to detect. We see only the brightest core regions, a tiny fraction of the galaxy's true glory. The galaxy contains over 1 trillion stars. This number is so large, it defies comprehension. If you could count 1 star every second, it would take you over 31,000 years to count 1 trillion. Each of those points of light represents a nuclear furnace, many with their own families of planets, some possibly harboring worlds where life has emerged and evolved. The sheer scale of possibility within Andromeda is staggering. These trillion suns are not distributed evenly. They cluster more densely toward the center, where the gravity of the galaxy's supermassive black hole and the accumulated mass of ancient stars create a crowded stellar metropolis. In the outer regions, stars are more widely scattered, drifting in lonely orbits through the sparse galactic suburbs. Between the spiral arms, fewer stars illuminate the cosmic dark, creating the beautiful pattern of light and shadow that defines Andromeda's structure. Andromeda is racing toward us through the darkness. Despite the vast distance that separates our galaxies, Andromeda is one of the few galaxies exhibiting a blue shift, meaning it is moving toward us rather than away. It approaches at a speed of about 110 kilometers per second, nearly 250,000 miles per hour. This might seem fast, but at such enormous distances, the galaxy appears almost motionless to our eyes, creeping imperceptibly closer year by year. In about 4.5 billion years, Andromeda and the Milky Way will collide. Computer simulations show this won't be the violent crash you might imagine. Stars are spaced so far apart that individual stellar collisions will be extremely rare. Instead, the encounter will be a gravitational dance of enormous grace and complexity. The two galaxies will stretch and distort each other, creating tidal tails of stars that curl outward into space like cosmic streamers. As the galaxies merge over billions of years, their supermassive black holes will spiral inward toward each other, creating ripples in space-time itself before finally combining into an even more massive dark giant. The resulting galaxy, sometimes nicknamed Milkomeda or Milkdromeda, will likely be a giant elliptical system, having housed the beautiful spiral arms that both galaxies possess today. Our solar system will survive this cosmic collision, but its fate is uncertain. It could be flung into a much more distant orbit from the new galactic core, or possibly ejected from the galaxy altogether into the lonely darkness of intergalactic space. If Earth still exists billions of years from now, its night sky will be spectacularly different, filled with the combined starlight of both galaxies during the merger, and possibly much emptier afterward if we're cast into the cosmic deep. At the heart of Andromeda sleeps a monster, a supermassive black hole known as M31 contains the mass of 100 to 140 million suns, concentrated into a region smaller than our solar system. This is far more massive than Sagittarius A star, the black hole at our galaxy's center, which weighs only 4 million solar masses. Yet despite its enormous size, Andromeda's black hole is strangely quiet, one of the least active known supermassive black holes in the nearby universe. The black hole emits very little radiation, suggesting it feeds on a slow, steady diet of gas and dust rather than violent meals of disrupted stars or gas clouds. Material spirals toward this dark heart in long, filamentary structures, like cosmic water going down an invisible drain. Recent studies show these feeding streams stretching across thousands of light years, gradually delivering matter to the event horizon, where it vanishes forever from our observable universe. Data from the Chandra X-ray Observatory revealed that the black hole has been in an elevated state of X-ray activity since a major flare in 2006. These occasional outbursts may be linked to material falling past the event horizon or to magnetic field interactions in the accretion flow. Some researchers have even suggested a possible connection between flares from Andromeda's black hole and high-energy neutrinos detected by the IceCube Neutrino Observatory on Earth, though this remains highly speculative. Surrounding the black hole lies one of the most puzzling features in astronomy: Andromeda's double nucleus. For decades, astronomers observed what appeared to be two bright centers in the galaxy's core. Hubble Space Telescope. Observations finally resolved this mystery. What seems to be two nuclei is actually a single galactic center, P2, surrounded by a brighter elliptical ring of older red stars, P1, that orbits the true center. This ring of ancient suns itself contains a nested disk of younger, hot blue stars spinning at incredible speeds of 2.2 million miles per hour around the sleeping giant at the galaxy's heart. How these young stars, formed so close to the supermassive black hole, remains a mystery. The environment near the black hole should be too hostile for star formation. Yet there they are, about 400 bright blue stars racing in tight orbits through one of the most extreme gravitational environments in the local universe. Andromeda is classified as a barred spiral galaxy, though this wasn't known until infrared telescopes like Spitzer could peer through its dust lanes. At its center lies a prominent bar-shaped structure of stars, a glowing bridge that rotates slowly and helps funnel material toward the central regions. This bar structure is common among spiral galaxies and plays a crucial role in their evolution, stirring gas and dust, triggering star formation, and feeding the central black hole. The bar has a distinct boxy or peanut shape when viewed from the side, creating what astronomers call an X-shaped structure. This geometry likely formed from the galaxy's central bar, buckling and puffing upward over billions of years, sculpted by the complex gravitational forces of billions of stars orbiting in resonance with each other. Infrared observations revealed that the bar structure is nested within other galactic components, creating a complex, layered architecture in Andromeda's central regions. The stars along this central bar have a metallicity similar to our Sun, meaning they contain similar abundances of heavy elements forged in previous generations of stars and scattered by ancient supernovae. The galaxy's spiral arms are being warped and distorted by the gravitational pull of its companion galaxies. These arms are not the neat, symmetric structures they might appear to be from a distance. They twist and bend under invisible forces, creating patterns more complex than a simple pinwheel. Unlike the arms of our Milky Way, which appear to have 4 major spiral features, Andromeda displays at least 2 main spiral arms that appear tightly wound around the galactic center. These spiral arms trace regions of active star formation, marked by bright blue stars and glowing gas clouds. A prominent ring of dust and star formation lies about 32,000 light-years from the galactic center, like a cosmic ring of fire slowly turning in the dark. This ring may have been created by an ancient collision with the galaxy that became M32, a violent encounter that left lasting scars in Andromeda's structure. The galaxy's overall star formation rate is lower than expected for a galaxy of its size, suggesting it may be transitioning to a less active state. Like an aging star that has burned through much of its nuclear fuel, Andromeda appears to be settling into a quieter middle age, still forming stars, but no longer in the urgent rush of its younger days. This reduced activity may reflect the galaxy's turbulent past. Major mergers and collisions can disrupt star formation by heating and dispersing the gas reservoirs that feed stellar nurseries. Andromeda is surrounded by a vast family of smaller galaxies. At least 35 dwarf galaxies orbit it like cosmic moths circling a flame, though cosmological models predict there should be many more faint dwarf galaxies that have yet to be discovered. These satellite galaxies are bound to Andromeda by gravity, following long, slow orbits that take millions of years to complete. The two most prominent companions are M32 and M110, both visible through small telescopes on clear nights. M32 is a compact elliptical galaxy believed to be the stripped-down core of a larger galaxy that plunged through Andromeda's disk billions of years ago. This ancient collision was catastrophic for the intruder. Most of its stars were torn away and scattered, leaving behind only the dense central region we see today. This violent encounter may have created several features we observe in Andromeda today: the ring of dust in the galaxy's disk, the warped spiral arms, and possibly even some of the complexity in the central regions may all be scars from this ancient collision. M32 serves as a reminder that galaxy evolution is often a violent process, shaped by encounters and mergers that reshape entire stellar systems. M110, discovered by Caroline Herschel in 1773, is a dwarf elliptical galaxy that drifts more peacefully in Andromeda's gravitational embrace. Unlike M32, M110 shows no signs of violent disruption. It has maintained its structure while slowly orbiting the larger galaxy, occasionally passing through the outer regions of Andromeda's disk in a stately gravitational dance. Perhaps most mysteriously, many of Andromeda's satellite galaxies orbit in a vast, thin plane, all rotating in the same direction, a configuration not predicted by current models of galaxy formation based on dark matter simulations. This plane of satellites extends across hundreds of thousands of light years and includes most of the brightest dwarf galaxies in Andromeda's system. Even more puzzling, all but one of Andromeda's 37 brightest satellites are located on the side of the galaxy that faces toward us, toward the Milky Way. This lopsided distribution suggests that the gravitational influence of our own galaxy may be affecting the arrangement of Andromeda's companions across millions of light years of space, or that both galaxy systems are embedded in larger dark matter structures that shape their satellite populations. The galaxy's history is written in stellar streams. Andromeda has grown over billions of years by consuming smaller galaxies, a process that continues today. The remnants of these ancient meals can be seen as vast streams of stars in Andromeda's halo, ghostly ribbons of light that trace the orbital paths of galaxies that no longer exist. These stellar streams are extremely faint and difficult to observe, but they tell the story of Andromeda's cannibalistic past. Unlike our Milky Way's relatively calm history, Andromeda shows signs of a more violent and chaotic past, filled with significant mergers that have shaped its current structure. Evidence suggests Andromeda underwent a major collision with another large galaxy between 5 and 9 billion years ago. This titanic encounter helped forge the complex, multi-layered structure we see today, mixing stellar populations and redistributing gas throughout the galaxy. The remnants of consumed galaxies can be identified by analyzing the chemical composition and orbital motions of stars in Andromeda's halo. Different stellar populations carry the chemical fingerprints of their birth environments, allowing astronomers to trace which stars originally formed in Andromeda and which were accreted from smaller systems. This cosmic archaeology reveals a galaxy built from the accumulated debris of numerous smaller galaxies over billions of years. Some of these ancient mergers may have triggered episodes of intense star formation, creating bursts of new stars that temporarily brightened the galaxy. The aftermath of these starbursts can still be seen in regions where hot gas was blown out by stellar winds and supernovae, creating cavities and bubbles in the interstellar medium that persist for millions of years. Andromeda is home to a rich system of globular clusters, dense, ancient balls of stars that orbit in the galaxy's halo. With approximately 450 to 500 of these stellar cities, Andromeda hosts more globular clusters than our own galaxy. These clusters contain some of the oldest stars in the universe, relics from the early epochs of galaxy formation, when the first generation of stars was lighting up the cosmic dark. The most massive and luminous globular cluster in Andromeda is called Mayall 2, or G1, which is also the brightest globular cluster in the entire local group of galaxies. G1 contains several million stars packed into a sphere only about 180 light-years across. It's so massive that some astronomers believe it may be the remnant core of a dwarf galaxy consumed by Andromeda long ago, its outer stars stripped away by tidal forces. These globular clusters show a much wider range of ages than those in the Milky Way. While our galaxy's clusters are uniformly ancient, typically 10 to 13 billion years old, Andromeda's span from incredibly old to relatively young, just a few 100 million years. This diversity tells the story of a galaxy that has continued to capture and cannibalized smaller systems throughout its long history, acquiring new clusters with each merger. In 2005, astronomers discovered a new type of extended star cluster in Andromeda. These clusters contain as many stars as globular clusters, but spread across much larger volumes, hundreds of times less dense than traditional globular clusters. They represent a class of stellar assembly unknown in our own galaxy, possibly formed through different processes or in different environments than classical globular clusters. The brightness distribution of Andromeda's globular clusters is used as a standard candle to help measure distances to other, more remote galaxies. By comparing the apparent brightness of Andromeda's clusters to similar objects in distant galaxies, astronomers can gauge the vast scales of the universe and trace the cosmic distance ladder that extends to the very edges of the observable cosmos. The brightest star cloud in Andromeda is designated NGC 206, a massive region filled with young blue stars. This stellar nursery glows with the light of ongoing star formation, a reminder that despite its ancient age and violent past, Andromeda continues to birth new suns from the gas and dust that flows through its spiral arms. NGC 206 spans several hundred light years and contains enough mass to form millions of stars over its lifetime. Within this star-forming region, dense clouds of molecular hydrogen serve as stellar wombs, slowly collapsing under their own gravity to form new stars and planetary systems. The most massive stars in these regions burn hot and bright, living fast and dying young in spectacular supernova explosions that enrich the surrounding gas with heavy elements and trigger new waves of star formation. Andromeda's interstellar medium contains about 54 million solar masses of dust and at least 7.2 billion solar masses of neutral hydrogen gas. This material, invisible to optical telescopes, but detectable in radio and infrared wavelengths, forms the raw material from which new stars are born. The dust grains, composed primarily of carbon and silicon compounds, play a crucial role in cooling gas clouds and shielding the delicate early stages of star formation from disruptive radiation. The galaxy is surrounded by a massive, nearly invisible halo of hot gas that stretches about 1 million light years from the galaxy, extending halfway to the Milky Way. This gaseous envelope contains half the mass of all the stars in the galaxy itself. A vast reservoir of material heated to millions of degrees by shock waves, stellar winds, and the gravitational energy of infalling matter. This hot halo is invisible to optical telescopes, but glows softly in X-rays and ultraviolet light, revealing the galaxy's much larger, hidden structure. The halo serves as a reservoir for future star formation and a record of the galaxy's past activity. Gas heated by ancient starbursts and supernova explosions rises into the halo, where it cools over millions of years before potentially falling back onto the disk to fuel new generations of stars. The discovery of this extended gaseous halo fundamentally changed our understanding of galaxy structure and evolution. Most of a galaxy's matter exists not in stars, but in these vast, hot envelopes that extend far beyond the visible disk. The halo's properties encode information about the galaxy's formation history, its interactions with the intergalactic medium, and its role in the larger cosmic web of dark matter and gas. Andromeda rotates, but not as a solid wheel. Different regions orbit at different speeds, with the inner areas completing rotations much faster than the outer reaches. This differential rotation has helped shape the spiral arms and contributed to the formation of the central bar structure over billions of years. The rotation curve, a plot of orbital velocity versus distance from the center, reveals the distribution of both visible and dark matter throughout the galaxy. Near the center, stars orbit rapidly due to the strong gravitational pull of the central black hole and the dense concentration of stars in the bulge. In the disk regions, where most stars reside, orbital velocities remain roughly constant with radius, indicating the presence of an extended dark matter halo that dominates the galaxy's mass. In the outermost regions, velocities may decline, suggesting we're seeing the edge of the dark matter distribution. This rotation pattern creates the galaxy's spiral structure through a process called density wave theory. The spiral arms are not fixed structures, but rather patterns of enhanced density that rotate at a different speed than the stars themselves. As gas and stars pass through these density waves, they are compressed, triggering star formation and illuminating the spiral pattern with bright young stars. Besides its central supermassive black hole, astronomers have detected at least 34 other stellar mass black holes within Andromeda. These are the collapsed cores of massive stars, each weighing several times more than our Sun, scattered throughout the galaxy like dark seeds of gravitational power. They betray their presence through their interactions with companion stars, heating material to millions of degrees as it spirals into their event horizons. Some of these stellar mass black holes exist in binary systems, slowly consuming material from a companion star. Others drift alone through the galaxy, invisible and undetectable except through their gravitational effects on nearby objects. The actual number of black holes in Andromeda is likely much higher. These 34 represent only the ones bright enough and active enough to be detected by current instruments. Neutron stars, the dense remnants of slightly less massive stellar explosions, are also scattered throughout Andromeda. Some of these spin rapidly and emit beams of radiation, creating pulsars that act like cosmic lighthouses. These objects are so dense that a teaspoon of neutron star material would weigh about 1 billion tons on Earth. White dwarf stars, the cooling remnants of sun-like stars, populate the galaxy by the billions. These Earth-sized objects represent the ultimate fate of most stars in the universe, including our own sun. In Andromeda, some white dwarfs exist in binary systems where they slowly accrete material from companions, occasionally erupting in nova explosions that temporarily brighten them by factors of thousands. In 1999, a microlensing event in Andromeda called PIA 99N2 suggested the presence of a planet orbiting a star in that distant galaxy, with a predicted mass about 6 times that of Jupiter. If confirmed, it would be the first extragalactic planet ever discovered, a world orbiting a star in another galaxy so far away that its light takes 2.5 million years to reach us. The detection relied on gravitational microlensing, where the gravity of the planet and its host star briefly magnified the light from a more distant background star. This technique is extremely difficult to apply at such vast distances, and the observation remains uncertain. However, it represents a tantalizing glimpse of the possibility that planets are common throughout the universe, even in galaxies far beyond our own. Given the trillion stars in Andromeda, the galaxy almost certainly hosts billions or even trillions of planets. The same physical processes that created the solar system, the collapse of gas and dust around newly formed stars, should operate throughout the galaxy. Some of these worlds might have conditions suitable for life as we know it, though detecting them directly remains far beyond current technology. The search for life beyond Earth includes the possibility that some of Andromeda's trillion stars may host biospheres. While we lack the ability to detect signs of life at such enormous distances, the galaxy's vast stellar population suggests that if life is common in the universe, Andromeda almost certainly harbors worlds where biology has emerged and evolved. Some regions of Andromeda show evidence of past starburst episodes, periods when star formation proceeded at rates much higher than normal. These bursts may have been triggered by gravitational interactions with companion galaxies, by gas flows from the intergalactic medium, or by internal instabilities that compressed gas clouds and sparked intense stellar nurseries. The aftermath of these starbursts can be seen in expanding shells of hot gas carved out by stellar winds and supernova explosions. These superbubbles can grow to enormous sizes, punching holes in the galactic disk and venting hot gas into the halo. The energy from massive stars can regulate star formation by heating and dispersing the gas that would otherwise collapse to form new stars. Young stellar associations in Andromeda trace out the galaxy's spiral arms, marking regions where star formation is currently active. These associations contain hot, blue stars that burn through their nuclear fuel quickly, living only a few million years before exploding as supernova. Their brief lives make them excellent tracers of recent star formation activity. The galaxy's magnetic field threads through its disk and halo, though it's much weaker than Earth's field. This galactic magnetism influences how cosmic rays travel through the galaxy and how gas clouds collapse to form new stars. Magnetic fields can provide pressure support against gravitational collapse, regulating the efficiency of star formation and shaping the structure of the interstellar medium. Studying these magnetic fields requires sensitive radio telescopes that can detect polarized emissions from cosmic ray electrons spiraling through the magnetic field lines. The field structure appears to follow the spiral arms in some regions, while showing more complex patterns in others, reflecting the galaxy's turbulent history of star formation, supernova explosions, and gravitational interactions. Cosmic rays, high-energy particles accelerated by supernova shock waves and other violent processes, stream through Andromeda's interstellar medium. These particles, mostly protons and atomic nuclei, travel at nearly the speed of light and carry enormous energies. They interact with gas clouds, magnetic fields, and stellar radiation, creating a web of high-energy processes that influence the galaxy's evolution. Some cosmic rays escape Andromeda entirely, contributing to the background radiation that fills intergalactic space. Others are confined by the galaxy's magnetic field, bouncing back and forth through the disk and halo for millions of years before finally escaping or losing their energy to interactions with gas and radiation. Radio waves from Andromeda reveal structures invisible to optical telescopes. Cold hydrogen gas throughout the galaxy emits characteristic 21-centimeter radiation that radio telescopes can detect, mapping the distribution and motion of gas that doesn't show up in visible light. This radio emission traces the galaxy's rotation, reveals the warped structure of its outer disk, and highlights regions where gas is being compressed or disrupted. Pulsar signals from rotating neutron stars provide precise cosmic clocks scattered throughout Andromeda. These rapidly spinning remnants of massive stars emit beams of radio waves that sweep across space like lighthouse beams. By timing the arrival of these pulses, astronomers can study the interstellar medium, test theories of gravity, and probe the magnetic field structure of the galaxy. The galaxy emits neutrinos, ghostly particles that barely interact with matter, from nuclear reactions in stellar cores, from cosmic ray interactions in the interstellar medium, and from supernova explosions. Trillions of neutrinos from Andromeda pass through your body every second, carrying information from the galaxy's most extreme environments. These particles are so weakly interacting that they pass through the entire galaxy almost unimpeded, providing a unique window into otherwise hidden processes. Neutrino observatories on Earth occasionally detect these particles from cosmic sources. Though distinguishing neutrinos from Andromeda from the much brighter flux from our own sun and galaxy remains extremely challenging. Future neutrino telescopes may be sensitive enough to study high-energy processes in distant galaxies, opening an entirely new window on extragalactic astronomy. Gravitational waves, ripples in space-time itself, occasionally pass through Andromeda from the merger of black holes or neutron stars elsewhere in the universe. While these waves are too weak to be detected at intergalactic distances with current technology, they represent another messenger that carries information about violent cosmic events throughout the universe. The galaxy's chemical evolution tells the story of successive stellar generations. The oldest stars in Andromeda contain only small amounts of elements heavier than hydrogen and helium, reflecting their formation in the early universe when few previous generations of stars had lived and died. Younger stars show progressively higher abundances of carbon, oxygen, iron, and other heavy elements produced by nuclear fusion in stellar cores and scattered by supernova explosions. This chemical enrichment process operates differently in different parts of the galaxy. The central regions, where star formation has been most active over the galaxy's history, show the highest metallicities. The outer regions and the halo contain stars with lower metal abundances, reflecting their formation in less chemically evolved environments, or their capture from smaller, less massive galaxies. Some stars in Andromeda show unusual chemical signatures that mark them as immigrants from smaller galaxies that were disrupted and absorbed over cosmic time. These chemical fingerprints allow astronomers to trace the galaxy's accretion history and understand how it assembled its current mass through the capture of smaller systems. The interstellar dust in Andromeda plays a crucial role in the galaxy's evolution. These tiny grains, composed primarily of carbon and silicon compounds form in the atmospheres of dying stars and are dispersed into space by stellar winds and supernova explosions. The dust absorbs and scatters starlight, creating the dark lanes visible in optical images of the galaxy. In cold, dense regions of the interstellar medium, dust grains provide surfaces where hydrogen atoms can combine to form molecules. These molecular clouds, enriched with water, carbon monoxide, and more complex organic compounds, serve as the birthplaces of new stars and planetary systems. The dust also helps cool the gas by radiating away thermal energy, allowing clouds to collapse under their own gravity. Infrared telescopes can detect the warm glow of dust heated by nearby stars, revealing star formation activity hidden behind opaque dust lanes. These observations show that much of Andromeda's ongoing star formation occurs in regions invisible to optical telescopes, emphasizing the importance of multi-wavelength astronomy for understanding galaxy evolution. Complex organic molecules have been detected in Andromeda's interstellar medium, including polycyclic aromatic hydrocarbons and other carbon-based compounds that form some of the building blocks of life. These molecules are created in stellar atmospheres and modified by interstellar radiation and chemistry, suggesting that the chemical precursors of biology may be common throughout the galaxy. The discovery of these molecules raises intriguing questions about the potential for life in Andromeda. While the galaxy is far too distant for us to detect biosignatures directly, the presence of organic chemistry in its interstellar medium suggests that the raw materials for life may be widely distributed among its trillion stars. Time moves differently when viewed on galactic scales. The light reaching us tonight from Andromeda's front edge arrived about 65,000 years before the light from its back edge, due to the galaxy's vast size and its tilt relative to our line of sight. We're seeing different parts of Andromeda at different moments in its past, watching a time-distorted view of our cosmic neighbor. This light travel time effect means we're observing Andromeda not as a single moment frozen in time, but as a composite image spanning tens of thousands of years of the galaxy's history. The spiral arms we see today may have rotated significantly since the light we observe was emitted, and star formation regions may have evolved or dissipated entirely. When astronomers study the motion of stars and gas in Andromeda, they must account for these light travel effects to understand the galaxy's true three-dimensional structure and dynamics. The galaxy is not static, but constantly evolving, with gas flowing inward and outward, stars forming and dying, and gravitational interactions reshaping its structure over cosmic time. For a long time, Andromeda was considered a near twin of the Milky Way. But we now know there are many key differences in their mass, structure, and history. While both are spiral galaxies in the same local group, they have followed different evolutionary paths, shaped by different encounters, different gas supplies, and different internal dynamics. Recent measurements suggest that while Andromeda appears larger and more luminous than the Milky Way, our galaxy may actually be more massive due to a more extended dark matter halo. This has implications for the future collision between the galaxies. The more massive galaxy will play a dominant role in determining the dynamics and outcome of the merger. The differences between the galaxies extend to their satellite systems, their star formation histories, and their chemical evolution. Andromeda shows evidence of more violent mergers in its past, while the Milky Way appears to have assembled more gradually through the accretion of smaller systems. These differences make both galaxies valuable laboratories for understanding the diverse paths of galaxy evolution. Andromeda's satellite galaxies themselves show interesting differences from those around the Milky Way. Some of Andromeda's dwarfs are unique in the local group, having formed stars early in their history and then continued to do so, unlike the satellites around the Milky Way, which stopped forming stars long ago. This difference may reflect the varying gravitational environments and gas reservoirs in the two galactic neighborhoods. The large-scale environment may also play a role in these differences. The local group exists within a larger structure called the local sheet, a flattened arrangement of galaxies that may influence the behavior and evolution of individual galaxy systems. Andromeda and the Milky Way are the dominant members of this group, but their evolution has been shaped by interactions with smaller galaxies and the overall gravitational environment of the local group. As we look toward the future collision, computer simulations predict that the merger will result in the formation of a giant elliptical galaxy. Both the Milky Way and Andromeda will lose their beautiful spiral arms, transformed into a single, massive, egg-shaped system. The collision will trigger bursts of star formation as gas clouds collide and compress, temporarily brightening the merged system before it settles into the quiet old age typical of elliptical galaxies. The timescale for this merger is almost incomprehensibly long. In 4.5 billion years, the Sun will be nearing the end of its main sequence lifetime, swelling into a red giant that may engulf the inner planets. Earth's oceans will have boiled away, and any life that survives will have evolved forms unimaginable today. The collision between Andromeda and the Milky Way will unfold over a cosmic stage where the very nature of life and intelligence may have transformed beyond recognition. During the merger, the night sky as seen from Earth, if it still exists, will be spectacular beyond imagination. The two galaxies will fill the heavens with their combined starlight, creating auroras of stellar fire across the cosmic dome. New bursts of star formation will light up regions where gas clouds collide and compress, while tidal streams of stars arc across the sky in graceful curves sculpted by gravity. Our solar system will survive this cosmic collision, but its fate is uncertain. It could be flung into a much more distant orbit from the new galactic core, spending its future in the sparse outer regions of the merged galaxy. Alternatively, it might be ejected from the galaxy altogether, cast into the lonely darkness of intergalactic space where the night sky would be nearly empty of stars. If our solar system is ejected during the merger, future inhabitants of Earth would see a sky devoid of the familiar band of the Milky Way. Instead of the rich star fields we know today, they would look up at a sparse scattering of nearby stars against the profound darkness of intergalactic space. The merged galaxy would appear as a distant, fuzzy patch of light, too far away to resolve individual stars. The supermassive black holes at the center of both galaxies will eventually spiral inward toward each other, releasing gravitational waves that ripple through space-time itself. These waves will carry away orbital energy, causing the black holes to move closer together in an accelerating dance that culminates in their merger into an even more massive, dark giant. This black hole merger will be one of the most energetic events imaginable, briefly outshining the entire merged galaxy in gravitational wave radiation. The resulting black hole may be kicked out of the galactic center by the asymmetric emission of gravitational waves, wandering through the merged galaxy as a rogue supermassive black hole. The Triangulum Galaxy, M33, the third largest member of our local group, might also participate in this cosmic collision. Its ultimate fate remains uncertain. It might orbit the newly merged galaxy before being absorbed itself much later. Or it could be flung away into the cosmic deep by the gravitational chaos of the merger. Computer simulations show a range of possible outcomes depending on the precise initial conditions and the role of dark matter in the collision. Galactic collisions like this are relatively common throughout the universe and represent a key part of how galaxies grow and evolve. What seems catastrophic to us is simply another chapter in the long story of cosmic evolution, a process that has been shaping the universe since the first galaxies formed in the aftermath of the Big Bang. The merger between Andromeda and the Milky Way will not be the end of the story. The resulting elliptical galaxy will continue to evolve, potentially capturing other galaxies in the local group and slowly consuming its remaining gas reserves. Over tens of billions of years, star formation will gradually cease as the galaxy exhausts its fuel, leaving behind a collection of cooling stellar remnants in the far future. Yet individual stars will almost never collide during the merger. The space between stars is simply too vast. Instead, they will be thrown into new, chaotic orbits by the immense gravitational forces, like cosmic pinballs bouncing through a slowly changing maze of gravity. Some stars will be flung into the outer reaches of the new galaxy, while others might be pulled toward the center or ejected entirely into intergalactic space. The gravitational interactions during the merger will also affect planetary systems throughout both galaxies. Some planets may be stripped from their host stars by close encounters with other stellar systems. Others might have their orbits dramatically altered, potentially rendering them uninhabitable or moving them into more favorable zones around their stars. Even now, Andromeda continues to reveal new mysteries to astronomers studying it with increasingly sophisticated instruments. The Hubble Space Telescope's detailed observations have revealed individual stars across much of the galaxy's disk, allowing studies of stellar populations, variable stars, and the galaxy's detailed structure. Space-based infrared telescopes have peered through dust lanes to map star formation and reveal the galaxy's hidden architecture. Future telescopes will probe even deeper into Andromeda's secrets. The James Webb Space Telescope may be able to study individual star formation regions and giant molecular clouds in detail, while extremely large ground-based telescopes will resolve even more stars and trace the galaxy's chemical evolution through detailed spectroscopy. Radio telescope arrays are mapping the galaxy's neutral hydrogen gas and molecular clouds, revealing the raw material for future generations of stars. These observations show how gas flows through the galaxy, how it's affected by stellar feedback and supernova explosions, and how it feeds the ongoing cycle of star formation and stellar death. Andromeda serves as a crucial template for understanding how spiral galaxies form and evolve. Because it's close enough to study in detail, yet far enough away to see in its entirety. This galaxy provides insights into galactic processes that astronomers can then apply to more distant systems scattered throughout the observable universe. The galaxy's role as a cosmic laboratory extends to testing our understanding of dark matter and galaxy formation. The distribution of stars, gas, and dark matter in Andromeda provides constraints on models of how galaxies assemble and evolve within the cosmic web of dark matter that underlies the large-scale structure of the universe. Recent surveys have mapped the three-dimensional structure of Andromeda's stellar halo in unprecedented detail, revealing streams and substructures that trace the galaxy's accretion history. These observations provide direct evidence for the hierarchical assembly process predicted by dark matter simulations, where large galaxies build up through the merger and accretion of smaller systems. The satellite galaxies of Andromeda also serve as probes of dark matter physics and galaxy formation. Their number, distribution, and properties provide tests of cosmological models and constraints on the nature of dark matter itself. Discrepancies between observations and predictions have led to new insights into the complex physics of galaxy formation and the role of feedback from stars and black holes. Andromeda's position in the local group makes it a key player in understanding the dynamics and evolution of galaxy groups throughout the universe. The gravitational interactions between Andromeda, the Milky Way, and their satellite galaxies provide a laboratory for studying how galaxy systems evolve and merge over cosmic time. The galaxy's approach toward the Milky Way is already having subtle effects on both systems. Gravitational forces between the galaxies may be influencing the distribution of their satellite galaxies and the flow of gas in their outer regions. These effects will grow stronger as the galaxies draw closer, eventually leading to the dramatic merger that will reshape our cosmic neighborhood. Despite its enormous size and vast stellar population, Andromeda remains just one galaxy among hundreds of billions scattered throughout the observable universe. Each of these island universes contains its own population of stars, its own history of formation and evolution, its own unique story written in the patterns of light and darkness. Yet Andromeda holds a special place in human understanding of the cosmos. It was the first galaxy proven to exist beyond our own, the key that unlocked our modern view of the universe as a vast collection of galaxies stretching to the limits of observation. In its ancient light, we see not just a distant galaxy, but a mirror of our own cosmic heritage and a glimpse of the magnificent universe we are privileged to call home. The matter in Andromeda's stars, like the matter in your own body, was forged in the nuclear furnaces of earlier stellar generations. The carbon, oxygen, and heavier elements that make up planets and life were scattered into space by ancient supernovae, then gathered into new stars and worlds. In this way, Andromeda shares a common heritage with everything around you. We are all made from the ashes of stars. As you rest tonight, consider that Andromeda continues its slow approach through the darkness. Every year, it draws about 50,000 miles closer to us, a distance that seems enormous by human standards, but represents just a tiny fraction of the vast gulf that separates our galaxies. This approach has been continuing for billions of years and will continue for billions more before the galaxies finally meet. The journey to understand Andromeda is also a journey to understand ourselves. By studying this distant galaxy, we learn about the processes that shaped our own cosmic neighborhood. We discover how galaxies form, evolve, and interact. We glimpse the larger structures of the universe and our place within them. We come to appreciate the vast scales of space and time that dwarf our everyday experience, yet somehow gave rise to the conditions that made our existence possible. Somewhere among Andromeda's vast stellar population, on worlds orbiting alien suns, other forms of consciousness may have emerged and evolved. These hypothetical beings would see our Milky Way as we see Andromeda, a faint spiral of light in their night sky, approaching slowly through the cosmic dark. They might wonder, as we do, about the nature of galaxies and the possibility of life beyond their cosmic home. The light from Andromeda that reaches us tonight carries within it the stories of 1 trillion suns, the chemical signatures of stellar evolution, the traces of ancient collisions and ongoing star formation. Each photon that enters your eye has traveled for 2.5 million years across the vast emptiness between galaxies, surviving the journey from another world to reach you in this quiet moment. In the deepest sense, you are connected to Andromeda across the vast distances of space and time. The elements in your body and the energy that powers your thoughts originated in stellar furnaces, not unlike those that continue to burn in that distant galaxy. You are part of the universe's way of understanding itself, a conscious observer in a cosmos filled with wonders beyond imagination. Tonight, as you drift toward sleep, know that you're part of a cosmic story that spans billions of years and trillions of stars. The same physical laws that govern the motion of galaxies also govern the atoms in your body. The same forces that will eventually bring Andromeda and the Milky Way together are the forces that hold you to the surface of your planet, that keep the electrons in orbit around atomic nuclei, that bind the molecules of life together. As the night deepens and the stars wheel overhead, Andromeda continues its patient journey through the dark. Its trillion suns burn quietly in their distant spiral arms. Its central black hole sleeps in gravitational silence. Its companion galaxies dance their slow orbital ballet. And somewhere in the spaces between stars, cosmic rays and neutrinos stream through the galaxy, carrying information from stellar cores and supernova explosions, from the violent birth of heavy elements and the quiet death of ancient suns. Dream well of distant galaxies and cosmic collisions, of trillion-starred spirals dancing through the dark. Dream of the vast patience of cosmic time, of the stellar furnaces that forged the elements of life, of the gravitational forces that will one day reshape our corner of the universe. Dream of Andromeda, our magnificent neighbor, approaching slowly through the eternal night, carrying within its spiral arms the stories of cosmic evolution and the promise of transformation yet to come. Good night.